Hello, my name is Freya Olsen. I'm a postdoc at the Virginia Tech Center for Ecosystem Forecasting. And in this VERA forecasting challenge tutorial, I'm going to talk about the anatomy of a VERA forecast submission, as well as some other terminology that you're going to need to get started with the forecasting challenge. Within this video, I'll introduce some key challenge terminology. We'll discuss what's needed for a VERA forecast submission, and also describe some other data that are available to help you with your forecasting. The first key term is targets. When we talk about targets, we're thinking about two key things. Firstly, these are the historical observations that have been measured at our forecast sites. And second, this is ultimately what we're trying to forecast. These data can be used to train a model. But due to the real-time nature of the forecasting challenge, the targets are constantly being updated as new data are being collected. These data are also what will be eventually used to evaluate your forecast once the data are collected and made available. In a simple diagram, it might look something like this, where we have a time series of observations of a particular variable. In a data frame, it might look something like this, that is in a long format, where we have columns that are identifying our observation. These include the date, time, the depth of the measurement, and the site that the measurement is for. We then have a duration column, which describes over what period the measurement is for. The P1D here describes a daily measurement. We then have our variable names that include the name of the variable, the units of that measurement, and then a statistic. So for this particular example, we have temperature measured in degrees Celsius, and this is a mean. And the statistics refers to that particular duration. So this is a daily mean water temperature. Some other examples might include a sample where you take a single point within a particular duration. So a sample of a Secchi disk measurement is an example of a sample. And rain, for example, is a sum where the measurement is a sum across a particular day. So now that we have our observation targets, we need to think about what needs to go into a forecast of future conditions. Firstly, the forecast needs to include uncertainty. The forecast needs to follow a particular standardized format. And importantly, the forecast includes multiple axes of time. I'm going to discuss these by showing you some examples. The first way we can represent uncertainty is through a distribution. On this plot, we have the forecast that has in gray here, has a central value and some spread around it. If we assume that this forecast has a normal distribution, these values can be described by two parameters, a mean and a standard deviation. We can further describe this forecast by including the date that the forecast was generated. This is what we call the reference date time. In addition, we need information about the location of the forecast. So this is a forecast for FCR at 1.6 meters. We can combine these bits of information and when we're making our forecast. And so this is what might look as a kind of data frame. We have the date that is being forecasted. So you can see here in this example, it goes from the 2nd of May through to the end of May. And then we also have a reference date time. So the reference date time for a real-time forecast is going to be today, but for hindcasts or reforecasts, this might be a different day. Importantly, a forecast should only include a single reference date time. We again have the duration, which similar to the target represents the duration over which our forecast is relevant for. We have our site and our depth, which describe the location of our forecast. And then our representation of uncertainty is described in the family and parameter columns. So that normal distribution shown in the figure would be given a family of normal. There are multiple other distributions that are supported by the challenge, and you can look at the challenge documentation to see these. For every family, there are relevant parameters. So for that normal distribution, we have a mean or a mu value, and a standard deviation or a sigma. We have our variable again, which must follow the variable names as listed in the targets. We have our prediction, which are our actual forecasted values. And then we have some other descriptor columns, our model ID and our project ID. Another way we can represent uncertainty is through multiple simulations of the future. These are called ensemble members, which are described in the parameter column. All of the other parts of the forecast are the same. So we have that reference date time, which describes the date that the forecast was generated. So again, for real-time forecast, that's going to be today. We have our date time, our site ID, depth, and variables, all as described with the other type of representation of uncertainty. So this might look something like this. The columns are mostly the same. The ones that are going to change are going to be your family and parameter columns. So now with our multiple simulations of the future, our family is an ensemble. This is called an ensemble forecast. Our parameter column instead describes the ensemble member number. So for this 4 ensemble member forecast, these go from 1 to 4 for every date time. We again have our variable, our prediction, our model ID, and our project ID. To summarize, the VERA forecast must include uncertainty, and this can either be represented by a distribution or an ensemble. The representation of uncertainty is described in the family and parameter columns. So for a normal distribution, that would be a mu and a sigma. Next, the forecast submission must follow a standardized format, including the specific columns that I've shown you. The file must be a CSV, and you can help check your forecast file using the VERA forecast helpers package that can be installed into R from GitHub. Finally, the forecast must include these multiple axes of time, including a duration that describes the period that the forecast covers, whether this is daily, hourly, or monthly, and the values for the durations are listed in the challenge information. It includes a date time, which is the date that the forecast is for. And it also includes a reference date time, which describes the date that the forecast was generated. This is because the same date that is being forecasted can be forecasted on multiple days. So a forecast that is generated today for a week in the future will have the same date time as a forecast produced next week for the following day, but with a different reference date time. So now we've started to think about making our forecasts of our reservoir size. For many variables, what's happening outside a lake can be important in determining what's going to happen in the in-lake conditions. Within the VERA challenge, we've made access to weather forecasts a bit more straightforward so that you can start to integrate these into your forecasting workflows. The National Oceanic and Atmospheric Administration releases weather forecasts every day. And through the VERA Forecast Helpers package, you can access 3 different NOAA forecast data products that have been made available via the challenge. The NOAA forecasts are ensemble forecasts, and including 31 different realizations of weather conditions. So we have 2 different products that are future weather forecasts. We have the raw forecasts that are available from NOAA, which again is an ensemble forecast. So there's 31 different potential weather scenarios. And then we have our stage 2, which is kind of a process version of stage 1, where data have been made standardized and also made into an hourly input, which might be helpful for some forecasting frameworks. Finally, we have a stage 3 data product, which can be viewed as a historic data product. This is generated by stacking together all of the 1 day ahead forecasts to create kind of a pseudo observation and as a good estimate for the actual conditions historically experienced at the forecast sites. This can be really useful for model training and calibration and helps the handoff between kind of past training and future forecasting. Just as a visualization, you can see here we have multiple different forecasts, each having 1 day ahead all the way up to 9 days ahead, going forward into the future. And the stage 3 basically takes each of those 1 days and stacks them together into a time series that can be used for model training. Altogether, there are 8 different weather variables available within all of these data products. So to summarize, in this video, I've introduced some key challenge terminology. We've discussed the format needed for a VERA forecast, including representations of uncertainty and different axes of time that are present in our forecasts. And I've also described the different weather products available via the VERA Forecast Helpers package from NOAA. In the next video, we can talk about setting up the R environment so that you can run the tutorial materials, followed by a simple forecasting workflow via an R Markdown follow-along.